All right, it's 12:02, so we'll get started with the webinar. Welcome to this final webinar of OWC's Innovation Showcase Summer Series entitled Achieving Partial Denitrification with BioCord Reactors while Mitigating Nitrous Oxide Emissions. My name is Robert Nyman. I'm the Manager of Partnerships and Programs with the Ontario Water Consortium. I'm just going to run through a little intro and then we'll begin the webinar. The Ontario Water Consortium is Ontario's only sector support organization dedicated solely to water innovation. We bring together researchers, companies, municipalities, and governments to drive collaborative R&D, pilot testing, and real-world technology adoption. We bridge the gap between research and market-ready innovation. And while there are many innovation organizations across Canada, none are focused specifically and exclusively on water like OWC is. OWC's collaborative model delivers measurable results. Over the past decade, we've helped mobilize over $90 million in project funding, supported or created more than 350 industry jobs, and advanced nearly 80 water technology projects. We've partnered with more than 100 academic researchers and helped build infrastructure, including wastewater test beds in London and Guelph. We do this by connecting innovators with adopters and aligning the right funding, partnerships, and support to move solutions forward. Before we begin today's session, a quick note that although this is the final webinar in our Summer Innovation Showcase series, we'll be back this fall with our Academic Innovation Showcase series webinars. These sessions are currently being scheduled and will feature leading-edge research from across OWC's post-secondary partners, so we hope you'll join us again. You'll also see a QR code on the screen that you can scan and subscribe to the Ontario Water Consortium newsletter and stay informed about future events. Now, I'm very pleased to hand it over to Dr. Wudneh Shewa, Technical Solutions and Project Manager at Bishop Water, to begin today's webinar entitled Achieving Partial Denitrification with BioCord Reactors while Mitigating Nitrous Oxide Emissions. This technology was supported in part by the Ontario Water Consortium's Water Industry Growth Program, which concluded in the spring of 2024. Wudneh, over to you.
Okay, thank you, Robert. I'll first share my slide.
Yeah, we can see your PowerPoint.
Okay. Can you see that? Okay.
Oh, we can see it.
Okay. Okay. First of all, I would like to thank the Ontario Water Consortium for setting up this webinar. And also, I also thank the attendees showing interest and learn from us regarding the topics that already mentioned on partial denitrification and greenhouse gas emissions. Okay, so I would like to talk about the team. So this research was led by Dr. Martha Daniel and carried out at Biofilm Engineering and Water Resource Recovery Laboratory at Western University. And so as you can see, the team from our we have myself, Tony, and Kevin. And from the Western University, we have Lynn, Shabir, and Martha. So this work also was part of the PhD work of Lynn. And so all these team members have contributed to this presentation. Okay. So I would like now to briefly introduce about Bishop Water Technology. Most of you may be aware of our organization, but to briefly describe about our organization, we mainly specialize on wastewater treatment. And we have solutions like solids management and shoreline protection using a geotip technology, as you can see here. We have also a biological nitrogen removal systems using BioCord. In addition to that, we also have a phosphorus removal solution using a rare earth coagulant, which is called Clarifos. So we have been with these solutions for over 20 years. And yeah, so I'll just go to one of our main topics, which is the BioCord. So I'll be only touching one of our products, which is the BioCord. So as you can see here, the BioCord is a fixed film treatment system, and it's very simple and easy to operate. As you can see, it is made of fibers, polymeric fibers. It's made of, for example, polymers like polypropylene and other olefins, because they are known for their lightweight and also excellent chemical resistance. So in short, we can call this technology as a condominium for bacteria that adds a massive amount of surface area. So this is in short about the BioCord reactor. So if aeration is required, under the BioCord reactors, we have a fine bubble aeration if we are handling aerated biological treatment systems. Okay, with this brief introduction about BioCord technology and our product BioCord, I will just come to our today's presentation. So here you see the outline of today's presentation. I will start by introducing about the the greenhouse gas emissions, and then talk about pathways for N₂O production, and also touch the objectives of this study, the materials and methods used, and finally, I will cover the results. Okay, so as all of you may be aware of greenhouse gas emissions, there is increased greenhouse gas concentrations in the world, which is causing global warming, extreme weather, melting of ice, and also rising sea levels. So understanding these gases and their impacts is crucial for addressing climate change. So here you see a graph which shows the world production of greenhouse gas in the year 2022. As you can see here, totally 54 billion tons of carbon dioxide equivalent greenhouse gases have been emitted. So this graph shows all the components of the greenhouse gas, mainly carbon dioxide, nitrous oxide, and methane. So if we break down this graph into regions, you can see Canada's contribution around 782 million tons, European Union's 3,750, and for US, it's around 6,000 million. So now we are dealing with wastewater treatment, and the main and the potent greenhouse gas in wastewater treatment is N₂O. And as you know, its global warming potential is around 273, higher than carbon dioxide. That means if you have 1 kilogram of N₂O, the global warming potential is equivalent to 270 or 73 kilograms of carbon dioxide. So what should be done about this? So we have to mitigate this greenhouse gas. And as you know, on December 2015, Canada and also other 194 countries, they signed the Paris Agreement, which is an ambitious and balanced agreement to fight climate change. And the plan was to reduce the 2015 level of greenhouse emission by 25% in the year 2030. So every country will have also its own plans. Just only to see the plan from Canada is to reduce the GHG emissions by 40 to 45%. below the 2005 levels, and also to reach to net zero emissions by 2050. So as I have mentioned before, N₂O is our main topic. So as you can see here in this graph, based on the data from 2010 to 2019, the flux of N₂O, or the amount of N₂O per year, is around 0.3 million tons. And the contribution of wastewater in terms of percentage, as you can see here in this chart, this is the data from US. 60% of the N₂O comes from wastewater. So totally, globally, 0.3 million tons of N₂O is generated, and wastewater contributes around 6% of N₂O. Okay, so as I mentioned earlier, now I'll go and discuss about the pathways for N₂O production. So in biological wastewater treatment, there are three main pathways for N₂O. So the main objective in biological nitrogen removal is to convert this ammonia finally to nitrogen. So through this process, we have two main systems. The first one is nitrification, where ammonia is converted to nitrite. So through this process, we have intermediate products like hydroxylamine. So they may be converted to N₂O, and also after getting converted to nitrite, it may also go to N₂O. So there are two ways. So this may result because of higher ammonia oxidation, or it may be also due to low DO and because of different operational parameters. So we have here two pathways, and the other pathway is during denitrification process. So the denitrification process, as you know, it comes from nitrate to nitrogen. So, and it also consumes carbon. So we have an intermediate product like N₂O, which can be generated through the denitrification system. So our topic is on partial denitrification. So our main pathway will be the denitrification pathway. And so this may be happening because of low COD or low carbon, or it may be also due to low carbon, we can have N₂O in this case. Okay. So when we go into detail to the denitrification process, I just want to talk about partial denitrification pathway. So denitrification, as I've mentioned before, it's a microbial conversion of nitrite to nitrogen. But partial denitrification, as the name suggests, it is an incomplete conversion of nitrate. So as you can see, if you end at nitrite, then it is called partial denitrification. And here also I have to mention that the main advantage of partial denitrification is the nitrite can be a substrate for the anammox process. And you know, anammox process is a cost and energy efficient process for total nitrogen removal. So a successful PDN or partial denitrification process is characterized by the accumulation of nitrite. So if we end up in nitrite, note that we are also avoiding the N₂O generation. Okay, so to go further on the partial denitrification process, we did a lot of study on partial denitrification. We have studied the effect of different carbon sources, both external and internal, biofilm thickness, HRT, and different parameters. But we didn't investigate the greenhouse gas emission in our previous study, but in this study, we have mainly focused on the greenhouse gas emissions. So understanding and mitigating these emissions is also essential for achieving carbon neutrality and also addressing climate change, as I have mentioned before. Now let's go to the objectives of this study. So we have three main objectives. The first one is monitoring and quantifying N₂O. The second one is assessing the impact of C to N ratio on the performance. And the third one is evaluating the effect of scouring versus non-scouring. So we believe that this is the first study that investigated scouring versus non-scouring as far as biofilm reactors are concerned, and greenhouse gas emission is also concerned. So these are our main three objectives. So I'll go to the material and methods now. So this study has been carried out for more than 260 days, and we use two 2-liter reactors. As you can see, this is the BioCord that's inside the reactor. I'll come into details how the operational schemes look like. So we used a BioCord media of a surface area of 2.38 meters squared per reactor, and we have monitored the soluble COD, all the nitrogen fractions, and also we have collected the off-gas and also analyzed for different gas fractions, and usual pH, temperature, DO, and OR we have been also monitored. Okay, so I will not go to the details of all the study that we have conducted as far as partial denitrification is concerned. So our main focus for this presentation will be the last two phases. As you can see in the prior to the collection of studying of the greenhouse gas, we have tried to study the extent of PDN efficiency using different carbon sources. As you can see, acetate, methanol. We have also investigated different HRTs, different C to N ratios. So main focus for today will be the last two phases, where we have studied scouring and also C to N ratio. Okay, yeah, just to put it in a simple terms, for this study, the carbon source is acetate. The C to N ratio, we have used 1.5 and 3. And regarding scouring, we conducted without scouring and also with scouring. And mixing, we have been mixing the reactors continuously with argon gas at a rate of 25 milliliter per minute. By the way, this will also help us to maintain anaerobic condition. So to go more detail on the operation, let me go to, let me explain how we run our system. So we basically have had two reactors. The first one, we call it non-scouring reactor or our control reactor. And the second one is the scouring reactor. So in terms of mixing, as I have said, we use 25 milliliters per minute. So mixing happens in both the reactors, as you can see. But in terms of scouring, scouring is only happening in this in the second reactor. So the rate of the scouring is we do it daily for 2 minutes. So we purge it with 500 milliliter per minute of argon gas. So that's how the scouring is done. Other than that, we have synthetic wastewater for the nitrate feeding. Also, we have a carbon source. So what's left? So regarding the gas collection, so the off-gas emitted from the BioCord reactors is captured in gas bags, as you can see. And then we have analyzed for the different gas composition of which is emitted from the reactors. Okay, now let's go to the results. So before going to the results, I just want to mention about the conditions. I have already mentioned what such conditions we are using. So for all the reactors, we try to maintain nitrate loading of around close to 1 gram per meter square per day. But we varied the carbon using we varied the COD based on the C to N ratio, and also we are having scouring and non-scouring situations. So this is about the influent. Now let's go to the results. So I first mainly focus on the non-scouring system. So in the non-scouring system, as you can see, so we have 4 conditions. So I'm looking at the non-scouring system. As you can see here, in the first part of the study, which is with a C to N ratio of 1.5, you can see here the nitrate removal, the nitrate removed, and this the light yellow or the diluted yellow color indicates the nitrite accumulated, and the gray color indicates the N₂O emission. So the moment we increase the C to N ratio to 3, as you can see here, we eliminated all the N₂O. There was no N₂O emission in the C to N ratio of 3 operation. But unfortunately, in this case, we don't have nitrite accumulated. So there is a complete denitrification, we can say. So we want to have, as I've mentioned before, to be successful, we need nitrite accumulation as a feed to the anamorph process. So the take-home message from this is increasing CN ratio from 1.23 in this non-scouring system eliminated N₂O emissions. In addition, it enhanced nitrate removal. Nitrite is removed, but we had lower NO2 accumulation, and we eliminated N₂O emission from this system. Okay, now we covered the non-scouring system. Now let's go to the scouring system. In the scouring system, I will be describing it the way I described for the non-scouring system. So this one is with a C to N ratio of 1.5. So when we increase the C to N ratio to 3, so still there is N₂O production, but it is not as the one we saw in with C to N ratio of 1.5. So it is around 18% here, the N₂O emission, and in the C to N ratio, it's only about, on average, 3% of the denitrified nitrate. So you can consider we have close to 1 gram of nitrate. So out of that, how much nitrite and how much gas is produced. So the main advantage here is we have nitrite accumulation in the scouring system. Take-home message for the scouring system: when we increase the COD to a nitrate ratio, we enhanced nitrate removal. The good advantage is we have higher nitrite accumulation, and we have minimized or reduced the N₂O emission. So scouring increased the nitrite accumulation rate to a peak of 60% of denitrified nitrates, and also we have reduced the N₂O production to only 3%. Okay. So in summary, when we bring all the operating conditions and the results in one slide, as you can see, we have broken down all we have brought all the results here. So the best scenario based on our evaluation is C/N ratio of 3 with the biofilm scouring. So regarding N₂O emission, when we the COD to N ratio of 1.5 has higher N₂O compared to the C/N ratio of 3. And the scouring system has higher N₂O compared to the non-scouring system. So, and also in terms of impact, the C/N ratio has higher impact compared to the scouring of the system. Okay, so now I'll go to the just quantification of the greenhouse gas or the N₂O emission. We also monitored the carbon dioxide emission rate. Note that the dissolved oxygen, the oxygen and the methane values are very low in our system. It's an anaerobic kind of system, as I have mentioned before. So in terms of quantity, as you can see, the blue one, N₂O, carbon dioxide. So they have equal amount in terms of gram per meter square per day. But if we convert into the carbon dioxide equivalent, as I have mentioned before, N₂O is around 273 times CO2. So you can see here. So total greenhouse gas emitted is in red in terms of carbon dioxide equivalent. As you know, usually greenhouse gas emissions are expressed in carbon dioxide equivalents. So you can see the blue one is the N₂O, the red one is the greenhouse gas emission. So the difference is very small. So that difference is the contribution from carbon dioxide. Even though they have similar amount, but when we convert it into carbon dioxide equivalent, the impact of N₂O is very high. Okay, so further, just to finalize these results, we chose the last scenario where scoured biofilm only emitted around 3% of the partially denitrified nitrate and accumulated high nitrite nitrogen, which is about 60%. Okay, so before I come to the conclusion. So if you are interested to see the studies that we conducted on partial denitrification process, where we analyzed different carbon sources, and also we have microbial analysis and etc. A lot of work has been done, so you can refer to this study. And then finally coming to the conclusion. And yeah, before going to the conclusions, I just want to mention here that this research has been accepted by Journal of Environmental Management, and it's now under review. So to finally wrap up this study, so as I've mentioned again and again, out of 1 gram nitrate per meter square per day, the BioCord emitted up to 0.05 gram of N₂O per meter square per day. The COD to N ratio exerts more significant influence on emissions compared to the effect of scouring. Higher COD to N ratio of 3 effectively reduced N₂O emissions. Scouring increased the nitrate accumulation. And finally, biofilm with scouring at COD to N ratio of 3 accumulated high nitrite level and mitigated the greenhouse gas emissions. Yeah, so this is all about the presentation, and I would also like to acknowledge Ontario Water Consortium, because this study has been funded by OWC, and also MITAX was also involved in this study. And yeah, thank you for your attention, and let me know if you have any questions.
Yeah, thank you so much,
Wood. My time.
Thank you so much,
Yeah.
Wood, for the presentation. We now open the floor to the Q&A session. So you're able to either put your questions in the Q&A section of the webinar, or you could raise your hand and I can unmute you and you can talk directly to Wood. So now's your chance to pose any questions, any comments, anything you'd like to ask or connect with Bishop and Wood about. So we do have a question in the Q&A from Fatima, and she asked, thanks for the great presentation. What sludge ratio was used?
Yeah, say it again.
What sludge ratio was used? I think it says please.
Okay, so the C to N ratio, the maximum we used is 3. C to N ratio is of 3.
Right, thank you.
Mm-hmm.
Again,
so the main thing
else?
is, yeah, if we increase the C to N ratio, if we increase the carbon, we may eliminate the N₂O, but it will be not cost effective. We are increasing cost on the system. Yeah.
Would Fatima in the Q&A corrected herself and said, sorry, sludge recirculation ratio is what she meant.
Oh, okay, sludge recirculation. In our study, we are not recirculating the sludge. It's a continuous process. There is no sludge recirculation.
Thank you, Wood. If we have any other questions, you can either raise your hand or put them in the chat in the Q&A section. Give everybody a minute. Actually, there's another question from Fatima. Did you collect all off gas or only samples?
Okay, so regarding gas, we collect, for example, we collect for 2 hours per day. We just avoid the scouring time, and we collect a 2-hour sample, and then we convert it into daily production.
Thank you, Wood. Okay, we have a question that was posted in the chat because the Q&A wasn't working for that person, unfortunately. But the question here is, and it's from Brett Wagner. What were the ammonium and nitrate concentrations fed to the reactor? Would you expect anammox growth to decrease in N₂O emissions?
As I explained there, the amount of we didn't use any ammonia in our system, so because it's only the partial denitrification process. So you can consider close to 0 ammonia. In terms of nitrate, we are using around 35 milligrams per liter. But our design parameter is the amount that we load to the system, which is around 1 gram nitrate nitrogen per meter square per day. And regarding anammox, we have a further study follow-up of this. So we already have an anammox system following the 2 reactors I showed. So we are getting good results in terms of anammox. So that's my answer, if I answered your question.
I think, yes, it seems like he said thanks. I think he was asking whether the anammox growth, would you expect the anammox growth to decrease N₂O emissions? I'm not sure. Maybe that was part of your answer already.
Okay, so in terms of the pathway, the anammox will not make any impact on the N₂O because the N₂O gets generated from the nitrite. So the anammox, if we achieve anammox and we cut the N₂O, then let me open that slide, and that will explain. Oh, sorry, I have switched off my presentation.
Oh, good. I see something loading. We can see your presentation again.
Okay. So it all works down to the. Yeah, do you see my slide?
Yeah, we can see it.
Okay, so this is the pathway. So if we have ANAMOX process, the ANAMOX will use the nitrite and the ammonia, and it will go to nitrogen. So the advantage of the ANAMOX is just to consume the nitrite, which is generated out of the nitrate. So if we successfully achieve partial denitrification, if we end up in nitrite, then that's the way how the N₂O is mitigated. Okay.
Thank you, Wood. Do we have any more questions from the audience? Again, you can post them in the chat if you need to, if the Q&A is not working for you, or you can put it in the Q&A section, or you can raise your hand and I can unmute you to ask the question. Give everybody another 30 seconds to think about it. All right. It seems like
if you have also more questions, you can use the my email address and chat further.
Yes, and you can either reach out directly to Bishop, or you can reach out to the Ontario Water Consortium. We can always forward or connect you with Bishop for anything you want to talk about. Thank you, everybody, for being here. Thank you to Bishop Water and Wood for presenting today. It was a wonderful webinar. We appreciate your attendance and your questions, and we hope to see you again at a future webinar. Thank you very much, everybody.
Okay, thank you.
Thank you.